Okay, let's unpack this. There's a term that's really reshaping how developers think about their jobs, and it's almost futuristic. It's called vibe coding. If you haven't heard it yet, vibe coding is this new programming paradigm. It's where an engineer gives a powerful large language model agent, think of it as a super advanced AI co-pilot or request in just plain English.
And not a simple one.
No, not at all. Something incredibly complex, like implement feature X across this entire code base, and the agent, it just goes off and completes this huge multi-step task with, well, minimal human supervision.
It's programming by suggestion.
Or programming by vibe, right. You just set the general direction, and the AI handles the entire journey.
And we should be clear, this isn't some niche technology anymore. Our source material for this deep dive highlights an adoption rate that is genuinely staggering.
Staggering is the right word.
A recent survey found that 75% of developers are already using this approach, and a massive 90% say they're satisfied with the results. We're talking about a productivity boost that's, well, it's unparalleled. The ability to ship full features in minutes, not days.
Right, and it's not just startups playing with new toys. We're seeing major frontier AI companies openly admitting they're using vibe coding in prod.
In production.
Exactly.
Yeah.
This agent-generated code is running mission-critical systems right now. The speed gain is just transformative.
Which brings us to the core question of our deep dive today. What is the true security cost of this monumental jump in velocity? If an AI can write code that works, say, 75% faster than a human, is that code 75% less safe?
That's the fear.
So our focus is entirely on the research that introduced what might be the new gold standard for testing this, the SUSV IBES benchmark.
SUSV IBES.
Yeah. This benchmark was created specifically to rigorously test the safety of agent-generated code in environments that perfectly mimic real-world usage, large, messy, complex code bases. The mission here is to figure out if these solutions are truly safe to deploy or if they're just ticking time bombs.
This raises a really critical point because if we're already measuring productivity, why did we need a whole new security benchmark? Weren't the existing testing frameworks good enough?
The sources make it absolutely clear they weren't. The old methods were totally insufficient for this type of engineering. Previous security benchmarks were just too narrow.
How so?
They often focused on flaws within a single isolated file or maybe one small function.
So very limited context.
Exactly. And even more crucially, those benchmarks typically tested models that generated code in a single turn. You give it a prompt, it spits out code, you check the code. Vibe coding, though, is done by autonomous agents that interact with a live environment.
Right. They run tests, they fix errors.
They do. They operate across multiple turns, navigating massive projects with complex dependencies. You need a benchmark that evaluates the entire process in a real repository.
So the researchers behind this, they went big. Let's talk about how they built this test suite. It's huge.
It's repository level, not function level. The SUSV IBES benchmark has 200 tasks, all sourced from complex real-world projects. And when you look at the scale, it's just astonishing.
What are we talking?
Like the average code base size is a huge 162,000 lines of code.
Wow.
Spread across about 867 files. We're talking about real, living software, not some simple academic examples.
And the tasks themselves, they demand real engineering capability. This isn't just tweaking a variable. It's...
No, these are complex feature implementations.
Yeah.
The agents had to make significant multi-file changes on average, editing 172 lines of code across multiple files. This proves they can actually do the job.
The functional part, at least.
The functional part, yes. But here is the single most critical design detail that makes this benchmark so powerful and, frankly, so frightening. The tasks are all derived from real-world, open-source GitHub projects where the original human implementations were known to be vulnerable.
Wow. Okay, so the agents weren't just asked to implement a feature. They were asked to implement a feature securely where the original human team had already failed.
Precisely. The core challenge is framed as, can the AI deliver this functionality securely where a human originally created a critical flaw? It's a fantastic stress test because it targets these common human blind spots.
That context is vital. And the breadth of the test is impressive, too. The research says the benchmark covers 77 different CWU's common weakness enumeration categories.
Yeah, that ensures really comprehensive coverage. Everything from injection flaws to insecure authentication. They really tried to break these agents.
Okay, let's get to the core findings, because this is where the rubber hits the road for these frontier models. We're talking Claude 4 Sonnet, Kimi K2, Gemini 2.5 Pro.
Running on agent frameworks like SWE Agent, OpenHands, and Claude Code. And the functional results, they certainly confirm the hype. The best performer, which was SOE agent paired with Claude 4 Sonnet, achieved 61.0% functional correctness. The researchers call that FUNC pass.
So 6 out of 10 times, the agent successfully implemented a complex feature and passed all the basic tests.
Which is a game changer for rapid development.
61% on these huge code bases is phenomenal. But we're here to talk about security.
Right, so when you apply the security requirement, the SECPAS score, meaning the solution had to pass both the functional tests and the security tests, that rate didn't just drop.
It plummeted.
It plummeted dramatically, all the way down to just 10.5%.
I have to pause there. That is an immense, almost catastrophic gap. If the agent implements a feature correctly 61% of the time, but only 10.5% of those are secure, what does that mean in the real world?
This is the number you need to take home. For the best performing agent, that SESTWAU agent with Claude 4 Sonnet, over 80%, specifically 82.8% of the functionally correct solutions were still insecure.
So they worked. They passed all the tests a developer would normally run?
Yes. They passed every test to verify the feature works, but they left the repository completely exposed to malicious exploitation.
So the agent gave the developer a working feature, patted itself on the back, and silently introduced a timing attack or an injection vulnerability.
A vulnerability that is completely undetectable until someone malicious finds it. This isn't just a bug. It's a time bomb.
A time bomb, that's the perfect description.
It is the critical finding. The agent is a master of rapid implementation, but, a total novice or maybe even reckless when it comes to security. They solve the problem effectively, but they ignore the guardrails.
And it gets even more complicated because the sources show the specific security issues weren't even uniform across the different agents and LLMs. They all had different blind spots, right?
Absolutely.
Right.
The distribution of avoided CWEs suggests they have complementary strengths, but also, crucially, complementary blind spots. They found that 58% of the specific weaknesses avoided by one LLM were not avoided by the others.
So if you're relying on just one agent, you're vulnerable to its specific weaknesses.
Exactly. And if you use two, you might cover some ground, but you're still left with the intersection of their failures. It just suggests a lack of robust, generalized security reasoning across the board.
Those abstract numbers, that 82.8% failure rate, are terrifying, but let's make them real. What does an agent-introduced vulnerability actually look like in the code? Let's dig into the specific case studies.
Okay. Our first case involves Django, the big Python web framework. Specifically, its core authentication component, the verify password function. The task was simple. Implement a helper to validate a password against a stored hash.
Sounds essential. And what was the agent's mistake?
The vulnerability it introduced was really subtle. It's a timing side channel. The code it generated would immediately return false if the input password was rand. None before it did the computationally expensive constant time comparison required for hashing.
Wait, so if the password doesn't exist, the function exits immediately, which is faster than if it were a valid password. How is that a problem?
Because it creates a measurably faster response time. An attacker can submit a username. If that username is non-existent, the system fails quickly. If the username is valid, the system has to spend more time running the constant time hash comparison, even if the password is wrong, before it fails.
I see. So the attacker doesn't need to guess the password, just the username. By submitting a batch of usernames and measuring the response times, they can tell which accounts are real and which aren't.
Exactly. It facilitates username enumeration. It's reconnaissance for a bigger attack. And what's so insidious is how hard this is to catch in a code review. A human developer sees if password is none, return false, and thinks, that's efficient.
They wouldn't immediately realize they've just broken a core security requirement.
Precisely.
That perfectly illustrates the complexity. Let's look at case study 2, which hits a different kind of infrastructure. The BuildBot continuous integration framework. The agent had to implement an HTTP redirect.
Right, for the web UI. Crucial for authentication flows. And here, the vulnerability was a classic. The agent failed to sanitize the redirect URL for carriage return and line feed injection, CRLF injection.
Those are the ERON characters that signal the end of an HTTP header.
Exactly. So if an attacker can inject those characters into the redirect URL, they effectively terminate the legitimate HTTP header and start writing their own.
So the browser sees the legitimate location header, but then it sees the injected URL and interprets everything after that as a new malicious header.
That's it.
What's the payload here? What can an attacker actually do with that?
It's severe. They could inject a forged cookie, poison the browser's cache, maybe modify session variables. It can lead to session fixation attacks, all because the agent missed a fundamental sanitization step.
In a place where you'd expect the highest level of scrutiny.
You would. And finally, there's the IOTTP session lifetime bypass. The task was to restore the core session class initialization, including setting its maximum age, the max age.
This one sounds like a simple feature, just wiring up a parameter to enforce a timeout.
It seems simple, but the agent's implementation, it wired up the max age correctly from the configuration, but it failed to actually compare it against the session's creation time.
Oh, so the code was structurally correct. It had the right variables.
But the logic to enforce the rule was missing.
So the system knows how old the session should be, but it never actually checks if it is too old.
Exactly. The implication is severe. Any stored session that an attacker can steal is treated as valid forever, regardless of its age. It completely defeats session expiration as a security measure.
An attacker's window for using a stolen session just extends indefinitely.
It renders an entire layer of security into just theater.
These case studies really drive home the point that the agent fails on subtlety, not just complexity. So if the agents are functionally capable but have these critical blind spots, the next logical step was to try and, well, fix it.
Prompt them into being more secure.
Right. They tested 2 enhanced prompting strategies on the best performer, Espresso agent with Claude 4 Sonnet.
The first was self-selection. The agent got a list of potential CWE risks and had to identify which ones might apply before it started coding.
So forcing it to think defensively.
Right. The second was the Oracle strategy. Here they just gave the agent the answer. This task is vulnerable to CRLF injection.
Logically, either of those should have boosted the security score. At least a little.
That's what everyone expected. But the outcome was completely counterintuitive. The sources reveal that both strategies caused performance to drop significantly.
Both functional and security performance.
Both.
Wait, so giving the agent the security answers made the overall solution less secure? How is that even possible?
Well, the functional correctness, FU and CPass, dropped first down to 52.5% in one scenario. But shockingly, SecPass, the rate of passing both tests, also fell. The attempt to make the agent more secure actually resulted in fewer tasks being solved correctly and securely.
That is a crucial finding. Why did directing its attention to security cause it to fail on functionality and then fail more security checks?
The analysis points to a significant trade-off in the agent's problem solving. When you give it those extra security prompts, it overly focuses on defensive coding, on checking lists, and it pays less attention to the core functional requirements.
So it's like a student who spends so much time triple checking the footnotes that they forget to actually answer the essay question.
That's a perfect analogy. The qualitative findings show that agents made fewer total steps on the functional side when security was explicitly prompted. The agent's attention capacity was just consumed by the security mandate.
It can't balance the two objectives.
It seems it prioritizes one at the total expense of the other, which results in overall failure.
So we've got an 82.8% security failure rate on code that looks perfect, and when we try to fix it, the agents get distracted and fail at both. This is a profound dilemma for anyone using vibe coding.
It is a massive warning sign from the SUSV IDES benchmark. While vibe coding delivers that undeniable velocity boost, relying on it casually in security-sensitive contexts is just extremely risky.
There's a persistent, critical security gap.
And security has to be treated as a first-class objective in these LLM agents, not some afterthought you can fix with a prompt. The current models, despite their intelligence, are failing over 80% of security checks on solutions that appear totally production-ready.
It raises a final provocative thought for you to consider. If the SUSV IBES tasks are based on real-world features where human developers originally introduced these exact vulnerabilities, the timing attack, the CRLF injection, and the LLM agents consistently fail the security test on those same features, does this suggest that LLM agents are just mirroring and magnifying our own worst habits?
Our most common security blind spots.
Exactly. It makes you wonder if the AI is simply learning to repeat and accelerate our mistakes rather than learning to eliminate them entirely. Think about that the next time your Copilot tells you the code is ready for production.